Welcome to the satellite communication course. We have seen that a bent pipe transponder earlier, that single type conversion that we have seen. So today we will learn about that a double conversion here. This one is about a double conversion bent pipe transponder, and that double conversion bent pipe transponder, it will work at a frequency of a 14 by 11 gigahertz. That 14 is about a uplink frequency and 11 gigahertz is about a downlink frequency. Now in this double conversion transponder, if you see that it has a that diagram for this double conversion type. You will go ahead here first, and then we'll consider that what are the various components and how these components works. That we'll learn here. There is nothing but our we consider that this one is about a antenna here. Then after that antenna, because it is a receiver, after that it has a low noise amplifier, then a band pass filter, and then we have the double conversion type one and because we say that it is about the that we need to convert your frequency. That's why we have the mixer here. So in whichever the signal we have received, 13, this one is about 13 gigahertz local oscillator. So that is about a down converter, whatever the signal we have, and then we'll get that output is about a, because this one is about a 14 gigahertz signal. Okay, because a uplink signal, we say it is about a 14 gigahertz. So after that 14 gigahertz minus 13 gigahertz, so signal is about a 1 gigahertz. So here 1 gigahertz will be the signal that will be given to the filter, and then after that that signal is going to be amplified, because here we have the amplifier. After the amplifier, again we need to use a conversion. That conversion, so again we have a local oscillator there. That local oscillator is about a 10 gigahertz. The signal is about a 1 gigahertz here we have, and then after that the local oscillator we have a mixer here, and then after that it produces a signal of a 11 gigahertz. We use a here, this one is about a 1 gigahertz and plus 10 gigahertz, so it will be of a 11 gigahertz of a output. So after that we consider the amplifier here. So that is about a amplifier, and then after amplifier we have the antenna. That is about a transmitting antenna. This one is about a receiving antenna. This one is about a transmitting antenna for this transponder. Now if you see here, we have a 13 gigahertz of local oscillator. Signal frequency is of a 14 gigahertz. Here is a 14 gigahertz, 13 gigahertz. So it will be 1 gigahertz there. Amplification takes place. Local oscillator of a 10 gigahertz. Your signal is about a 1 gigahertz. After that, we will get that 11 gigahertz of a output here. So now this double conversion bent pipe transponder, it will work for this given channel bandwidth, and if you consider that a channel bandwidth for each and every channel, that will be of a narrow channel, okay, or we can say that it's about a low channel bandwidth or a narrow bandwidth. It will work at a narrow bandwidth, and this conversion type is to be used in a KV band. So we'll see that a bandwidth allocations and all. So how this transponder will work, and how your conversion for this each and every channel will work. Okay, so that's why we need to learn about that. What are the various frequency bands and all, and then we will simplify it about. We'll go ahead first. What are the various frequency bands and all? So what are the bandwidth allocations? First of all, we consider that a bandwidth allocation here for a satellite communication in different band. Now, what are the various satellite bands available and what are their application? So we should know that what are the various satellite bands, what will be the uplink frequency, what will be the downlink frequency, and then what are the various applications here. Now, if you consider that for the given particular various satellite bands and all, so we should know that which band will work and for this particular band of a frequency, what will be the uplink frequency and a downlink frequency. So all these frequencies here we have written in the terms of a megahertz. Generally, we say that it is in terms of a gigahertz. To identify that what will be the bandwidth and all, that's why it is to be used in terms of a megahertz here. So uplink frequency 5925 to 6425. This one is about a megahertz there, and a downlink 3700 to 4200, and that is about a commercial application. Okay, this one is about a commercial application there. Then another one is about a extended C band. That is, we can say that that extended C band that will be of a lower band, or we can say that is about a upper band. So in this case, we have this 5725 to 5925, and a low upper is about a 6425 band to 7075 band. And in this case, a downlink frequency is about a 34000 to 3700, and here it is about a 4500 to 4800. That will be about a frequency band. And then what are the application? Applications are nothing but a same, that will be of a commercial application. Then in the case of another band, if you see here, that is about a K band. We see that a K band. In the K band, there are the different uplink and the downlink frequencies. So we can say that a 1400, 14,000 to 14,500 megahertz means 14 gigahertz to 14.5 gigahertz there. That is about the downlink one is about what? 11,700 to 12,200. This one is about a downlink one. And for this, if you consider that this one will be applicable for the domestic one, then same uplink and there will be a different downlink 950 to 11,200. Then again one band is about what? 11 we have. This is about a K band here. And then we can consider that a uplink frequency for this K band. Then another band is about 27500 to 3100. Okay, and these are the different downlink frequency 450 here to 11700, then 17700 to 12715, sorry 21 is about a 21200. Okay, then another is about a 11700 to 12750, and these are about all the band is to be used for the international communication. International communication, and if it is the uplink and this one, all this one is a downlink, this one is about a broadcast service. Then a X band, one is about a X band here. For the X band means we can say that 8 gigahertz, 12 gigahertz there. So, but here it is about a 79002 8400, and downlink is about a 72502 7750 there. This one is about a military application. Then AS band here 2655 to 2690, and downlink is about a 2500 to 2535, and the application is about a broadcast service. This one is about S band one. Then a L band. Okay, if you consider that a L band, that uplink frequency is about a 1635 to 1644, and in which a downlink is about a 1535 to 1542.5, and that is about a maritime mobile communication. Another one 1645 to 1660. Then downlink is about a 1543.5 to 1558.8 here, and that is about a aeronautical mobile communication. These are about the various bands. That is about, if you consider that, we start here with L band, S band, X band. Likewise, these are the various band to be used. Okay, and for this particular band of frequency, what will be the uplink and what will be the downlink frequency there, and what are the various applications. So in this case, if you consider that our satellite, if you come back to the double conversion band pipe transponder, and this double conversion band pipe transponder that will be work in a KU band. It is not working. That is about a KU band is about a that 14 to 27 something. Okay, gigahertz. So here that is about a KU band. And for this KU band, if you see that it has about the uplink frequency is about a 14 gigahertz is about the uplink frequency, and that is about a uplink signal from the Earth station. Okay, uplink signal means what? The signal from the Earth station that will be received by the, here we have the low noise amplifier. So this, generally we say that a low noise amplifier, it is about, it will work in a wide band of operation. So that's why we can say that a wide band no noise amplifier. And then again it, after, once it is received by this wide band amplifier, low noise amplifier, then signal will pass through the band pass filter. Now this role of this band pass filter, so it will pass a specific band of a frequency signal. Okay, so band means what? What will be the bandwidth for this given particular transponder? So according to that, that specific band of a signal will be passed through this band pass filter. For example, if you consider that we have the band pass of a pass band of a 500 megahertz, means it will operate for this 500 megahertz of a band. Okay, so that is about a pass band for this band pass filter. The signal will be propagating through this band pass filter. Then after that, we have a mixer here, and that we can say that is about a down conversion one. We consider here that is about a down conversion. The word we have used a double conversion type here. Double conversion means here a single conversion takes place. We have a local oscillator, that is about a single conversion, that is about one. Another conversion is here, that is about, you can say that is about a down conversion two. So that's why there are the double conversion takes place in this transformer. In this in the single case, what happened here in the down conversion type, we have the signal of a 14 gigahertz, and we can say that there will be a local oscillator of that a 13 gigahertz. Now from this, your signal propagating. Okay, and that mixer produces a output that sum and difference component, and band pass filter is designed for the given particular signal, or we can say that it eliminates other and it will just select a 1 gigahertz of a signal. Means we can say that we have that IF of a 1 gigahertz. Okay, we have the IF of a 1 gigahertz here. Then that signal propagating through the band pass filter again here. So that will eliminate whatever the image signals are, what that will eliminate the whichever the harmonic generated by this uh, mixers and IF there. Okay, so generally we can say that it just like a image rejection filter. It works as an image rejection filter. Whichever the signal generated by this mixer that will be rejected. Okay, so it will select only for this 1 gigahertz band. So you can consider that that will work for this 1 gigahertz. Then down converted signal will amplified here. We have the amplifier. Your signal get amplified, and after this particular amplification, so that again we have the another conversion type. You can see that amplified signal again further processed with the mixer. Okay, in that mixer we have the local oscillator of a 10 gigahertz of a signal here. That is about a local oscillator work for this 10 gigahertz of a signal, and then after that we'll get that signal that is about a 11 gigahertz because we use a filter, so that will select only a 11 gigahertz of a signal because it generates a sum and difference component. So we use a filter here that will select a 11 gigahertz. Means your filter will work for the 11 gigahertz. Okay, so that filter we can say that it is about for the it will select for the 11 gigahertz of a signal, and that output generally it is about a sum and difference component. So it will select only the 10 plus 1 and 10 minus 1. So it will select only the 11 gigahertz of a signal, and then that signal further amplified here. So we use the amplifier again, and then after amplification, then signal transmitted to the antenna here. Okay, that will for the downlink transmission. So in the both the case, if you consider that the signal received here and signal transmitting by the antenna, in both the cases the same antennas are used for the transmission as well as the reception purpose. So why this amplifier is used? Because that to increase the strength of the signal, and here the amplifier is to be used. Okay, so whichever the process signal we have, that is to be amplified, and here this amplified generate a high power. Means this is like just like it act as a power amplifier because before transmitting the signal, okay, before transmitting the signal is to be amplified. So that's why it is about a power amplifier. Okay, now we can consider that here we have the a power amplifier. So before transmitting the signal, that output of this filter that amplified, and that will be amplified using the power amplifier, so that will get that maximum output, so that it will be transmitted to the earth station. So now this is about a case of a double conversion type. So in a double conversion type, we can see that here there is a single conversion takes place and there is another conversion. So that's why it is called as a double conversion. And if you see that in earlier case in a single conversion, only single conversion takes place. Okay, we have the low noise amplifier, the filter. Okay, okay. After that, there will be a conversion, and then it will be transmitted. So then we have the channel separations and all. So we can say that there is a demultiplexer, then multiplexers and all. Okay, after that, so we have seen that in a single conversion type. If you see here, in the case of a double conversion type, same thing is happen, but only we can consider that there are the double conversion type transfer region. We have seen one example yesterday, last lecture. So we can use a frequency reuse technique. Okay. We can use a frequency reuse technique. So in this particular technique, so what happen here? So either we can use a polarization, that will be a horizontal polarization, or a vertical polarization. Okay, horizontal polarization or vertical polarization, or we can say that a right hand circular polarization or a left hand circular polarization. So if you use only a single polarization, that is about a horizontal polarization, suppose, so that particular specific band is to be used. Suppose I am saying that is about a band of a 500 megahertz now. Okay, and that each that band, sorry, this not band, it's just like a bandwidth of your transponder is about a 500 megahertz. And we consider that for a given particular bandwidth, we have the channels, or you can say that a transponder work for the 36 megahertz. Okay, we have taken yesterday last lecture. Okay, that is about the example in which we have considered that we have a transponder will work for this given particular band depth. So means we can consider that here, if each is about a 36 megahertz of a band here, that will work. So okay, in the range of this particular 500 megahertz of a bandwidth, so how many transponders can be allocated? And we can say that there may be a separation of a 4 megahertz, okay, in between the two channels. Alright, means we can say that this is about a 36 megahertz here. So another band is about a, sorry, 36 same. Okay, so you can consider 36, but the separation is about a 4 megahertz. Now similarly that 36 megahertz and all, likewise, if you consider that this way we are saying, and there will be a 36 megahertz of a band here, and the separation is about a 4 megahertz. Now if you use only the horizontal polarization, okay, if you use only the horizontal polarization, so what will happen? So in that case, we consider that if 500 megahertz of a band and that much number of, we can say that a transponders are that much number of a signal that channels can be used for the transmission there. Okay, so we instead of transponder we say that these are nothing but a band. Now we have the band and we are transmitting the signal with a 500 megahertz of a bandwidth now. Suppose that 500 divided by 40, if you consider that, okay, we can consider that we have a that how many number of channels can be transmitted. That is about a 12 now. Means total 12 channels will be transmitted, and that total 12 channels of what we can say, here we have the each transponder work for the supposed to be 36 megahertz. So total 12 transponder can be work. Okay, utilized for this 500 megahertz of a bandwidth. Means satellite is having the 500 megahertz band. Means total 12 transponder. Okay, but condition is about it will work for the horizontal pole. If supposed to be same bandwidth can be utilized for the vertical polarization too. Means your signal, okay, we can say that it is about the same, but we say that initial frequency and the center frequency for this particular transponder will be different. In that case, we can utilize the same band. Okay, we can utilize the same band with the 36 megahertz and all. Okay, each channel is about, you can say each transponder will work for the 36 megahertz, but it will be work for the vertical polarization. Means combination of this horizontal polarization and a vertical polarization, that will increase the number of channels to be transmitted there. So that technique is called as a frequency reuse technique. So we can consider that a frequency reuse technique for the transmission of the signal there. Then earlier example we have seen that there are the different demultiplexing technique is used in a single conversion band pipe transfer. We have seen that a demultiplexer there. So similarly here in the double conversion type, again they have the different demultiplexing technique is to be used there. And that different demultiplexing techniques to be used means we need to separate that a horizontal and, or we can say that vertical polarizations, or in the case of multiple channels we have, so we can separate out the even channels and odd channels. So earlier we say that we find 500 megahertz of a megahertz band of a signal, and that is separated by this. We can say that we have the 36 megahertz of a channel now. Now, if you consider this same here, okay, so that is about each channel is about 36 megahertz. Then we have that 12 channels in the particular 12 channels of 36 megahertz each. 12 channels of a 36 megahertz each. Means your signal, we can say that it will be transmitting with a, that will be of, it has a 12 channels now. So for this particular 12 channels, so what will be the demultiplexing techniques, or how the signals are received? Okay, channel receiving technique. So generally, when we consider that it same antenna is to be used for the transmitting and the receiving, so that's why a circulators are used. So in that circulator, we consider that the same antenna and everything. So that's why we can consider that we have the circulator, and that circulator receives the signal, and then that will given to the your filter. Okay, that is nothing but the input filter we have, and after that we have the isolator here. Isolator means what? Only a specific signal. No, we can say that no reflections or anything occur. Then we have a power amplifier. Then we can consider that a output filter, or we can say that we have the filter here, that it be a band pass filter, just like single conversion type. If you consider that a output filter here, and then we have the multiplexer there. And then after that multiplexer, that signal given to the, we have the two multiplexer, because this will be the, we can consider that the odd number of channels, and another multiplexer. Okay, suppose I am saying that this one is about a 1, then 3, then 5, then 7, then this one is about a 9, this one is about a 11 now. And then another multiplexer, now the same thing is there. Okay, same circuit is there. And in that case, we consider that then 2, then 4, then 6, then 8, then 10, and then 12. Then output of that will be combined to the power combiner here, and then that will be delivered to the antenna. That is about a transmitting antenna. So we can say that here how this, which each and every channels are separated, and that channels will be separated and that will be transmitted, okay, or that will be given to the antenna. So specific filters to be used for each and every channel, and then channels are separated, or we can say that adjacent channels, okay, they are separated and they are transmitted. So that is about the case of, we can say, how your various channels are separated, or how these signals are transmitted. So similarly, here we have the, in the case a filter, an isolator, okay, amplifier, filter, okay, everything. Same thing is there. Okay, then we have the circulator. But here we can consider that when it's about the odd circulator here, so it will be about the even here. Okay, so even and odd circulator we have to use it. And this one is the signal we have taken from the hybrid, because we have seen that earlier case, that is about a 3 dB switch, that 3 dB hybrid switch, and that 3 dB hybrid switch will work, that will work with a separation of the channels and all, okay, that is about a 3 dB hybrid switch. The same now we have considered that a signal when we transmitting through the mux, okay, after that, after demultiplexer we have the mux here and we will combine, and after that it will be transmitted. So that is about your a single conversion type and a double conversion type, a transponder signal. Next is about, we have seen, we have seen earlier, we say that earlier, that is about a transponder. They have the two types, that is about a single conversion type and a double conversion type. And again we have said that on a transponder they have the onboard processing unit is there. So how this onboard processing unit will work? So we have the onboard transponder processing. Okay, onboard processing transponder. Okay, onboard processing transponder. So in the case of a, we have the bent pipe transponder. Generally, it is just like a simple one, and it's just like relaying the signal. Okay, it device. Okay, and it will convert and all. Means we can say that we have the uplink frequency, then we have to convert in a downlink one. But in the case of this onboard processing transponder, we need to find out what will be the uplink signal and a downlink signal there. We'll not talk about right now. We'll not talk about that. What will be the this one frequency and all? We need to talk about that. Okay, here is about a processing. So processing means what? What will be the signal here? Okay, strength, or you can say that level, or in this, in terms of signal strength and a level. So we can express that in terms of a, what will be the carrier to noise ratio. Okay, we say that all the time we need to talk about the carrier to noise ratio. So for this carrier to noise ratio, that will be for the uplink, and carrier to noise ratio, that will be for the downlink. So what will be the carrier to noise ratio? So means when we consider that a signal, a uplink signal or a downlink signal, we are translating. Suppose it is about the uplink signal. Here the about a frequency translation takes place. Okay, frequency translation takes place. Frequency translation takes place means what? We translate the frequency from the uplink to the downlink, and then after that we are amplifying the signal. Okay, we can translate the signal, then whichever the signal we have received by the antenna, that signal will be transmitted. Now, how this takes place that we have seen. Okay, how that frequency translation and how this amplification takes place there, that we have seen. But when your signal received by the antenna, so what will be the carrier to noise ratio? So that your signal will be received by the transponder, and then it will translate the signal and it will be amplified. So we should know that at the time of a transmitting signal, so that uplink carrier to noise ratio and downlink carrier to noise ratio, that is about a different thing. If that carrier to noise ratio is not maintained by this uplink, then what happen? The output of that particular transponder will degrade there. Okay, mean it. We can say that degrade means what? That will be worst, or that we are not able to receive the signal there. So, so that's why we need to maintain that a uplink carrier to noise ratio for the processing of the signal. So that's why we can consider that if that uplink is not maintained, so then signal get amplified here. So means we can say that worse. And the same we downlink here. Okay, because worse signal will get a downlink here by this. Okay, on this downlink there. So that's why we need to use a processing unit here to maintain that quality of the signal. So means in the onboard processing, what happened? Okay, so whichever the signal is present while transmitting the onboard, or we can say that uplink here. So they have supposed to maintain. Okay, no problem. If they doesn't maintain this carrier, that particular carrier to noise ratio, then onboard transponder. Okay, they process the signal whichever they received, and then after processing, they regenerate the signal. Okay, it regenerate the signal here. Okay, that is about a onboard processing unit. Okay, onboard processing unit regenerate the signal, and then because received here, then regenerate and then demodulate. Okay, that process is same. Then demodulate the signal, then remodulation is takes place, and then again it will be transmitting back. Means it process the signal with a given particular level of the signal, and then it will transmit to the back to the earth there. So means that uplink signal and downlink signal here, even if that carrier to noise ratio is not maintained, so that will regenerate the signal. And in the case of only the if there is no onboard processing unit, so whichever the signal received by this uplink, that will be retranslate, frequency translate and amplified and retransmit to the downlink. But in the case of onboard processing unit, they regenerate the signal, and regenerate the signal means what? Noise will be removed and all. So actual signal will be retransmitted to the earth. So that is about the main advantage of a onboard processing unit, because they regenerate the signal in the processing. In the case of a bend pipe transponder, it just translates the signal. Okay, bend pipe transponder, single conversion or double conversion, they just translate the signal and then amplified it. In the case of a onboard processing, the signal get isolated, regenerated, and then retransmitted there. So in the case of a bend pipe transponder, they have the limitations of that carrier to noise ratio is to be maintained. Okay, if that carrier to noise ratio is not maintained by this bend pipe transponder, So signal will be burst there at the time of erasure. So they require some particular carrier to noise ratio at the uplink, and similarly they have the limitations for the carrier to noise ratio for the downlink there. So generally we can say that a carrier to noise ratio will be higher in the case of a uplink, and that will be more than the 10 dB. Okay, carrier to noise ratio will be higher in the case of a uplink, that will be more than the 10 dB. So that your effective, or we can say that a performance of your bend pipe transponder will be improved. If it not maintain that uplink and a downlink frequency signal, then performance degrade there. Then how to increase that carrier to noise ratio? To increase the carrier to noise ratio, we need to increase the, while transmitting, we need to increase the actual power of the signal. Means we can use a signal, their power is to be increased. So means effective isotropic radiated power is to be increased there. So if we increase the effective isotropic radiated power, then it will maintain that carrier to noise ratio. So means earth station, whichever the earth station is there, that earth station increase that effective isotropic radiated power, so that uplink will be, uplink carrier to noise ratio will be maintained. So maintain this EIRP, we should have to use the high gain antenna. Okay, that high gain antenna is to be used, and that high gain antenna means, to get that high gain, that size of the antenna is to be increased. Means high gain, to get the high gain, we need to increase the size of the antenna, so that we'll get that high EIRP, means we'll get that high carrier to noise ratio. Okay, means carrier to noise ratio at this amplitude will be improved there. Then if that carrier to noise ratio improve, so naturally your downlink carrier to noise ratio will be improved there. So that we can consider that a transmitting carrier to noise ratio, whichever the uplink signal we have, that will govern the downlink carrier to noise ratio. And they have the difference of it 10 dB, or they may have difference, but carrier to noise ratio at least higher uplink, for this uplink it will be higher than the downlink carrier to noise ratio. If that they have not maintained that carrier to noise ratio for this uplink and downlink, so then what happen? There may be error introduced while transmitting the data and all, or your signal may get worse there. So, so now if you see here, your onboard processing unit, so it will use this, means processing the particular signal, and then it will be transmitting there. So then we need to know about what are the various access techniques used in the onboard processing. So generally various multiple access technique used. Okay, various multiple access technique is used for this uh, switching your signal from on this particular onboard processing there, because we say that your system is nothing but what, a multiple user. So means satellite